Hi, this is going to be a fairly short unit on Gaussian models and the perils of differential entropy. So let's start with Gaussian models. So let's look at the VAE, the definition of a variational autoencoder. When this was first introduced, all of the examples were using Gaussian distributions, or most of the examples. So we're considering the case where all of these are probability densities, Gaussian probability densities rather than probability distributions. So for example, the prior is a Gaussian centered at some mean, and I'm giving the distribution, the density for each component of Z, and we're going to allow in general, this is what's done, we're going to allow a different variance for each component of the vector. So we've got a diagonal covariance matrix that may not be the identity. So that's the prior. It's a Gaussian centered at some average in each position. The encoder is going to be computed in sort of two phases. The first phase is a deterministic computation of the encoding, this Z hat. So this is a particular point in the vector space. Then we take that point and we define a Gaussian centered at that point to be the actual density of Z given Y. So then the density becomes the distance from the point to this center that we've computed squared over twice the variance. And we get a different variance in each component. The decoder is defined exactly the same way. We take the encoding Z, we compute an estimate of the decoding, and then we define a Gaussian around that estimate in exactly the same way. So now all of these are smooth Gaussian densities. Now, densities, information theoretically, are tricky. They're kind of problematic. There's a definition of differential entropy, the entropy of a density function. So the entropy of a density is defined by, sort of in an analogous way to the entropy of a distribution. We take the expectation over the density of minus log the density, the probability density. So this is actually an integral now because we're doing things continuously. So it's an integral across all possible values of x of the density at that point times minus the log density. Now, just as an example, consider a uniform distribution on an interval of width, capital delta. So if it's a uniform distribution, the density is 1 over delta, so that it integrates to 1, delta times 1 over delta. Now, as delta goes to 0, the density goes to infinity. It's getting infinitely dense as the width goes to 0. And that means that this log 1 over delta gets greater than 1. And as this gets greater than 1, this becomes negative. So what's happening is as delta goes to 0, this notion of differential entropy is going to negative infinity. Differential entropies can be negative. The same thing happens with a Gaussian distribution. If you have a Gaussian distribution, you can sort of think of it as analogous to a uniform distribution whose width is the standard deviation of the Gaussian. And the same thing happens. This is just a calculation of the entropy of a Gaussian distribution in one dimension. And there's a log sigma here. And as sigma goes to 0, the entropy goes to negative infinity. So it's also sensitive to the choice of units. If I have a distribution on length and I measure those lengths in inches, then the density per inch will be smaller than if I measure it in feet and look at the density per foot, right? So exactly what the entropy of that distribution over lengths is depends on how you define the units. So let's consider what we do when we train a model, like let's say a Gaussian mixture model. And let's say that the Gaussian mixture model has a mixture of points, and it's estimating the covariance matrix of those points as part of the model. If the number of points is smaller than the dimension of the space, that covariance matrix will collapse on the subspace spanned by those points. And what's going to happen is the the cross entropy of our data to the model around for that cluster is going to go to negative infinity. And you're minimizing the cross entropy. So now you're minimizing something that's going to negative infinity. Ouch. It can be tricky. It's a little tricky to minimize something that goes to negative infinity. Another way to think about it is that differential entropy should really be thought of as being infinite. If you think in terms of Shannon's source coding theorem, right, that says that if I pick an element of this discrete distribution at random and look at how many bits it takes to name that element, then the optimal code is going to give you the number of bits plus or minus 1 equal to the entropy of that distribution. Now, if I draw a random real number like pi or the square root of 2, but if I draw one at random, and let's say it's between 0 and 1, that means if I represent it, it's going to be point something, something, something. It's point all of these numbers that are infinitely long. So the number of bits it takes to name that exact real number is actually infinite. So we want to think, it's appropriate to think of differential entropies as being actually infinite. However, differential KL divergence is much more well behaved, right? If I look at the standard formula for the KL divergence between two densities, that's defined in terms of the ratio of the densities. And the ratio of the densities is sort of insensitive to how finely I do my numerical integration, right? Once the numerical integration is fine enough, this is going to have a nice, well-defined limit as the, if I take a Riemann integral as the step size goes to 0, you're going to get an accurate estimate of this because it's got this ratio. So unlike differential entropy, differential KL divergence is always non-negative. It can be infinite, but it's always non-negative. For example, KL of a density to itself is always 0. This ratio is always 1 in that case. Now we're going to be talking about mutual information. We're going to have a whole section on mutual information. I just want to point out here that mutual information is a KL divergence and is meaningful for differential entropy. So intuitively, first let's consider just the discrete case. Intuitively, the mutual information between X and Y is the number of bits it's the reduction in the number of bits we need to name Y as a result of observing X. So it's technically defined to be by this formula. It's the expectation over drawing X and Y of their joint probability divided by the product of their marginals. And you can rearrange these terms this way. You can pull this P of Y out. And then this is just the entropy of Y. And this term is just the entropy of Y given X. So the mutual information is the reduction in how many bits it takes to name Y when I've learned X, right? How many bits do I save by learning X? So intuitively, it's how much does X know about Y, but really you need to rely on the formulas. This is a good one. This corresponds to, how many bits did I learn by learning X? About Y did I learn by learning X? And this is meaningful differentially. It's a KL divergence, right? You're drawing from the joint distribution and looking at a ratio of densities. It's also, mutual information is also useful in the data processing inequality. So the data processing inequality says that if I have a random variable Y and I compute some function of it, then two values of Y in the discrete case could go to the same value of Z. So intuitively, that's going to make the entropy of Z smaller. So the data processing inequality says that the entropy of Z is smaller than the entropy of Y, but that data processing inequality only holds in that form for discrete distributions. If we look at a density, I can take that density and F can either expand the distribution if it's continuous or contract it, right? Think of a function on the real line. If I scale it by a constant factor A, It makes a difference whether A is greater than 1 or A is less than 1. If I expand it, its entropy is going to go up. If I contract it, its entropy is going to go down. So the data processing inequality does not hold in that form. However, it does hold in a mutual information form. If I've got a function z of y, and I look at the mutual information, how much does y know about x, or how much does z know about x? If z is a function of y, then the amount z knows about x can't be any larger than the amount that y knows about x. The mutual information with x has to go down, can't be any larger. So there's a differential form of the data processing inequality. Okay, let's go back and look now again at Gaussian models for variational autoencoders, Gaussian VAEs. So this is the definition of a Gaussian VAE. Here I'm using phi for the combination of both the prior and the decoder. And this term right here is a KL divergence. I'm sampling from the encoder and looking at a ratio of the encoder probability and the prior probability. So this term is okay differentially. It's a KL divergence. This term, however, is a differential cross entropy, and that is somewhat problematic. And in particular, we're going to be looking at the case where this is a Gaussian, and I'm going to do the simple case where every component of the Gaussian has the same variance. So that'll just make the calculation simple. So this decoder density is this density, right? It's a Gaussian centered at this, and it has a sigma squared times the identity matrix as a covariance matrix. Now, if I just take negative log of that probability and optimize that with respect to my parameters, this variance is actually part of the decoder parameters, which I can optimize, and I'm supposed to be able to optimize the decoder parameters. And this parameter shows up here. It shows up in Z also. So if I take the log probability, I get something over here that's looking at the squared difference between what the decoder deterministically computed and what it's trying to match. So this is a nice squared difference. Now in practice, even though according to the VAE objective function, I should be able to optimize sigma, in practice people just ignore this term, and they ignore the fact that this is part of the parameterization of the decoder. But before we take that a little further, I want to point out that if y has units like inches, then this term depends on the choice of units again. So if y has units, we're a little problematic right here. If y is dimensionless, it's defined to be some dimensionless quantity, then this would be at least meaningful, or at least it would be well formulated independent of units. Okay, but in practice, people ignore this, and in practice, what happens is for Gaussian models, for Gaussian VAEs, this last term here in the VAE turns into just a distortion term with some arbitrary parameter stuck in front of it. So what I just showed you was the case where the distortion term is L2. It's just an L2 distortion. We're looking at the distortion between the reconstruction and the truth. And in practice, with a Gaussian model or any differential model, the differential cross entropy is really more meaningfully thought of as a distortion. And what we've seen is an L2 distortion. We just put a weight on this. But it's also common to use L1 distortion, where L1 distortion is just the sum over the components of the absolute value of the difference between these two. So that's a quick tour of differential entropy and how it's used in Gaussian VAEs, and I'll end there.